So far, we've been writing our queries against existing databases. But as a software engineer or database administrator, there are times when you will need to design a new database from scratch or add new tables to an existing database. And that's what you're going to learn in this section. I'm going to walk you through a simple step-by-step process to design well-structured databases. Remember, a well-designed database requires a bit of planning at the beginning and it may take a bit of time, but it plays a critical role in the success of your applications. If your database is designed properly, you can easily extend it to support new business requirements. You can easily query it to extract useful information and your queries will execute quickly. A poorly designed database requires a lot of maintenance and the cost of maintaining it increases over time to the extent that it will eventually prevent you from supporting new business requirements. In one of the companies that I worked at, we had a poorly designed database and believe it or not, some of our stored procedures were almost 1,000 lines of code because the structure of the database was overly complex, so extracting data was really difficult. Also, some of our queries took several minutes to execute. So in this section, I'm going to walk you through a systematic approach to design well-structured databases. Are you ready? Let's get started. In this lecture, we're going to talk about data modeling, which is the process of creating a model for the data that we want to store in a database. It involves 4 steps. The first step is to understand and analyze the business requirements. Unfortunately, so many developers skip this step and jump into creating tables in a database. But this step, in my opinion, is the most important step in the data modeling process. Yes, it's a bit slow and takes a bit of time, but the better you understand the business problem you're trying to solve, the better you can come up with a solution, in this case, a database. So before you think about your tables and columns, you need to fully understand the business requirements. You need to talk to the business stakeholders, domain experts, and even end users. Look at the existing forms, documents, applications, spreadsheets, databases, pretty much anything that is relevant to the problem domain you're working on. Once you collect all this information, your next step is to build a conceptual model of the business. And this involves identifying the entities or things or concepts in the business and their relationships with each other. A conceptual model is just a visual representation of these concepts that you use to communicate with the stakeholders so you know you're both on the same page. Once you have a conceptual model, you refine it to come up with a data model or data structure for storing data. This is what we call a logical model. A logical model is an abstract data model that is independent of database technology. It just shows you the tables and columns you need. Next, you refine this logical model to build a physical model for a specific database management system. So a physical model is the implementation of a logical model for a particular database technology. In this model, you should have the exact data types supported by your database technology, the default values for your columns, whether they're nullable or not, the primary keys for your tables, as well as other objects like views, stored procedures, triggers, and so on. So a physical data model is very specific to a database technology like MySQL. So this is the process of data modeling. Now, don't worry if all this sounds a little bit ambiguous. Over the next few lectures, I'm going to walk you through all these steps using a real-world example. Next, we're going to look at conceptual models. In the last lecture, you learned about the 3 types of data models: conceptual, logical, and physical. In this lecture, we'll be looking at conceptual models. So let's say we want to build a website for selling online courses so people can sign up and enroll in one or more courses. These are the video courses that online instructors like me upload to this website. A course can have one or more tags like front-end or back-end. Now, to create a database for this website, first, we need to create a conceptual model that represents the entities or things or concepts in this business and their relationships with each other. Quite often, these entities are things like people, events, locations, and so on. So what concepts or entities do we have here? Well, at first glance, I can quickly pick a couple of entities: student and course. These are the concepts that we need to know about in this domain. Now, we need a way to visually see these entities and their relationships. There are basically 2 ways to do this. We can use entity relationship or UML diagrams. These are both ways for visually expressing concepts. Entity relationship diagrams are often used for data modeling. UML is short for Unified Modeling Language, and its scope goes way beyond data modeling. Some people are more comfortable with UML diagrams, others prefer entity relationship diagrams. They're both equally good when it comes to building conceptual and logical data models. In this course, I'll be using entity relationship diagrams. Now, there are various tools out there for creating entity relationship diagrams. If you're on Windows, you can use Microsoft Visio. There are also a couple of popular online tools like Draw.io or Lucidcharts. So here on Draw.io, on the left side, we have various kind of visual languages like UML, entity relationship, flowchart, and so on. Now, under entity relationship, here we have this entity object. We can add this to our diagram. Let's double click and rename this to student. Now, inside this box, we list all the attributes that we need to know about each student. Things like their name, their email address, the date they registered, and so on. So let's double click here and list these attributes: name, email, date, registered. And note that here I'm using camel notation. So we capitalize the first letter of every word except the first word. This is purely my personal preference. You don't have to follow this convention. This is just a conceptual model that we use to communicate with stakeholders. You can use any naming conventions that you prefer, but keep it consistent, okay? Now, one thing you need to know is that data modeling is an iterative process. You can't come up with the perfect design in your first attempt. So you need to constantly go back and forth between the requirements and your models and keep refining them. So these are the attributes that we currently know about students, but they may change later. We may add new attributes or rename or remove some of these attributes. Now let's add another entity here, course. What attributes do we need to know about the course? We need to know its title, we need to know its price, the instructor, and tags. Next, we need to define the relationship between these two entities. So here we have various kinds of relationships, as you can see here. Now, don't worry too much about the difference between these types. You're going to learn about them soon. So here I'm going to select a many-to-many relationship. Let's drag and drop this here and attach the left side to the student box and the right side to the course box. There you go. Now let's give this relationship a label. So we double click it and type enrolls. So we read this relationship from left to right, saying student enrolls in course. So this is a conceptual model that gives us a very high-level overview of the business domain and the things involved in this domain. At this point, we don't have any details about the type of each attribute. Neither do we know or care what database management system we're going to use to implement this model. It's just a conceptual model. And we use this to communicate with the business stakeholders so we know we're both on the same page and we talk the same language. These are the benefits of conceptual models. Next, we're going to use this conceptual model to build a logical model. So we're going to continue with the conceptual model that we built in the last lecture. Now we're going to refine this model to come up with a data model or a data structure for storing our data. This logical model is independent of database technologies. That's why we call it a logical data model. It's just an abstract data model that clearly shows our entities and their relationships, but it's a bit more detailed than this conceptual model. Later, when we pick a database management system like MySQL, we'll refine this logical model to implement it for this particular database management system, okay? So, what are we going to have in this logical model? Well, first we need to specify the type of each attribute, like string, integer, float, date, and so on. For example, the student's name is a string, so here in parentheses, we type string. Note that here we have a string, not varchar, because varchar is an implementation detail. It's a data type in MySQL. But this logical model is independent of database technologies, okay? Now, similarly, email is a string, so let's add that here as well. And date registered is a date time. Now, it's often a good practice to split an attribute like name into multiple attributes like first name and last name. With this, we can easily query or sort students by their first or last name. In contrast, if we have a single attribute to store the full name, then we'll have to deal with extracting the first or last name, and this will make our queries complex and slow. The same is true when you have an address attribute. You should break it into smaller pieces like street, city, zip code, country, and so on. This way you can query on these individual pieces, okay? So let's split the name attribute into first and last names. That is better. Next, we need to specify the type of the relationship between our entities. We have three main types of relationships: one-to-one, one-to-many, and many-to-many. The other types are variations of these three types. In this case, we have a many-to-many relationship between the student and the course, because a student can enroll in multiple courses and a course can have multiple students. Now, if you want to change the type of this relationship, we can select it. And here on the right side, we have this panel. From this drop-down lists, we can select the type of the relationship. Now, you see a lot of different shapes here because Draw.io supports a lot of different visual languages. Some of these icons are part of UML. So down the bottom, you can see the icons for entity relationship diagrams. If this is confusing for you, you can also hover your mouse over each of these relationships. So this is a one-to-one relationship. Here's a one-to-many relationship, and so on. Okay? So in this logical model, we should clearly specify the type of relationship between our entities. At the conceptual level, this doesn't matter. All we need is a straight line between entities. The type doesn't matter, okay? Now, there is something missing here. What if we need to know the date a student enrolled in a course? Where should we put that data attribute? We can put it here on the student because a student may enroll in several courses. Then we need a separate attribute for each course. And we won't know ahead of time how many courses each student is going to enroll in. That doesn't make sense. What if we put it on the course entity? That doesn't make sense either, because the enrollment date would be different for each student. So the enrollment date is not an attribute of the course. It's an attribute of the enrollment, right? So it's an attribute of the relationship between the student and the course. This is a common scenario in the real world that a lot of data modelers don't get right. So here we need to introduce a new entity that represents the relationship between the student and the course. Let me add that here and rename it to enrollment. Now in this entity, we're going to have an attribute called date. And the type of this attribute is date time. Now we need to delete this relationship between these two entities and recreate it through this new entity. So select this, delete. Now a student can have many enrollments, but each enrollment is for a particular student. So here we have a one-to-many relationship between the student and the enrollment. So I'm going to pick this relationship on the left side, add it here. Now let's drag and drop it on the student and the enrollment. So a student can have multiple enrollments, and that is why we have this fork icon on this side. This represents many, right? Similarly, a course can have multiple enrollments, but each enrollment is for a particular course. So once again, we need to add another one-to-many relationship here. Let's move this around. So I'm going to attach this end to the course entity and this other end to the enrollment. So one to many, okay? So previously we had a many-to-many relationship between these two entities. Now we have two one-to-many relationships. You see that a lot in modeling relational databases. All right, so now we have a new entity that clearly represents an enrollment for a student in a particular course. In this entity, currently we only have one attribute, that's the date. But let's say we talk to our domain expert and we realize that courses are priced differently over time. So each student may buy a course at a different price. Where should we put that price? In the enrollment entity. That is the price a student pays at the time of enrolling in a course. So let's add another attribute here, price. And the type of this should be float because we can have digits after decimal point, like $49.50. Once again, at this level, we don't care what is the name of the corresponding data type in MySQL or any other database management systems. That's why we use float. Now in MySQL, we're going to use decimal. In another database management system, we might have a different type. Our logical model doesn't care. This is just an abstract data structure. So compare our conceptual model with our logical model. Our conceptual model doesn't really give us a structure for storing data. It only represents the business entities and their relationship. And we use it to understand the problem domain and communicate with the domain experts. Our logical model adds more details to our conceptual model. So now we almost know what structure or what tables we need to store our data. The entities that we have here eventually end up as tables in our database. All right, now let's add the type for these attributes as well. So title is going to be a string, price is going to be a float, instructor is going to be also a string, and tags, we can keep things simple, so we can use a string, and if a course has multiple tags, we can separate them using a comma. Now, you might say, Mosh, this is not a good idea. I know, we're going to talk about it later when we get to normalization. So for now, let's keep things simple. Next, we're going to take this logical model and implement it in MySQL. As I told you earlier, a physical model is the implementation of a logical model for a specific database technology. So in this lecture, we're going to take our logical data model and create a physical data model for MySQL. So here in MySQL Workbench, on the top, let's go to the File menu and select New Model. Now, this EER that you see here is short for Enhanced Entity Relationship. So here we can also create entity relationship diagrams. Now, by default, this model assumes a database called MyDB. We can right-click this and go to Edit Schema to rename it. So let's change the name of this database to School. Now, we haven't created a database yet. This is just a model or a physical model for that database, okay? Now, on the top, let's add a new diagram. In this diagram, we can add tables and views. So here's the icon for adding a new table. Let's click this and add it here. Now let's double click this and rename it to something meaningful. In this case, students. Now, when it comes to naming tables, I personally prefer to use plural names because a table is a container for several entities like students. Some people prefer to use singular names for their tables, and they have their own valid reasons. Whatever you prefer, go for it, but stick with that convention. If there's already a convention in place, follow that. Don't break the rules. It's much better to stick to the existing convention, even if it's not ideal. Otherwise, your development and maintenance cost is going to increase pretty quickly. You have to constantly remember if a table name is singular or plural. So in my logical models, I use singular names for my entities, and in my physical models, I use plural names for my tables. All right. Now let's add columns to this table. First, let me zoom in a little bit so you can see clearly. That is better. Now I'm going to close the Navigator panel. So here's our table designer. Here we can add the columns in this table. Now back to our logical model. Here are the columns that we need to add: first name, last name, email, and date registered. So first I'm going to add the first name, first underline name. So here I'm following a different convention. That is a MySQL convention. We separate multiple words using an underscore. Now the type of this column is going to be varchar of, let's say, 50. So as I told you before, I use standard lengths for my strings. So for shorter strings like username, password, first name, I use 50. And for medium length strings, I use 255. This is just my personal preference. Now you can see by default, MySQL marks this column as a primary key. We don't want this to happen. We're going to talk about primary keys later. So for now, let's uncheck this box. Now here, this column is marked as not null. So we cannot accept null values in this column. That's good. Now let's add the second column. Last name, also varchar of 50. We want to mark this column as not null as well. Now let's add the email, also varchar of, maybe 50 is not enough here because perhaps some people's email is longer. So I'm going to go with 255. And also we want to mark this as not null. And finally, we're going to add date underline registered. And for this, we're going to use a date time so we can store both the date and the time the student registered. Also, we want to mark this as not null. So at this level, in this physical model, we have the exact types in MySQL. We also know if columns are nullable or not. We can also set the default values. This is the difference between a physical model and a logical model that is independent of database technologies, okay? So here's the end result. This is our students table. Now it's your turn. Add the other entities that we defined in our logical model to this physical model. For now, don't worry about their relationships, just add the tables and their columns. You'll see my solution next. All right, here's my solution. So we have two new tables, courses and enrollments. In the courses table, we have title of type varchar of 255. For the price, I have used decimal of 5 and 2, and that means we can have a maximum of 5 digits with 2 digits after the decimal point. So the maximum price that we can allow here is $999. Now, how did I come up with this? Let's say I talked to the business stakeholders. So they told me that the maximum price they want to allow on their website is $999. Now, if this rule changes in the future, we can always come back and fix this. So I didn't go for a decimal of 9 and 2 right from the get-go because that would waste our disk space. As I told you before, keep things small. Next, we have instructor. For the instructor, I have used varchar of 255. We could go less, like 50 characters, but I just wanted to be on the safe side, so that's why I used 255 characters here. And also for tags, I have used varchar of 255 characters. Now, all these columns are required, so we do not accept null values. Here we have the enrollments table with two columns, date and price. Note that I have called this column date, not enrollment date, because this is a little bit repetitive and redundant. I've seen a lot of data modelers prefixing their column names with a table name like enrollment date and enrollment price. This is really unnecessary and makes your code ugly. Date is an attribute of enrollment, not enrollment date, okay? So just a little side note, now the type of this column is date time, so we can store both the date and the time someone enrolled in a course. And the price column in this table is also a decimal of 5 and 2. So look at the consistency between these tables. All right, we're not done yet. Next, we need to add a primary key to each table and define the relationships between these tables. All right, now we need to add a primary key to each table. As you know, a primary key is a column that uniquely identifies each record in a given table. So what column can we use here to uniquely identify each student? We cannot use the first name because many people can have the same first name. The same is true for the last name. What about the combination of the first and last names? This is what we call a composite primary key. A composite primary key is one that has multiple columns. Again, here we cannot rely on the combination of the first and last names because two people can have the same full name, John Smith and John Smith. What about the email? Well, email certainly uniquely identifies each student, but the problem with the email is that it can be several characters long. So as you will see shortly, when we add a relationship between these two tables, this primary key in this table, in this case, email, is going to be repeated in the enrollments table. So every time a student enrolls in a course, his primary key, in this case, email, is going to get repeated in the enrollments table. And that is not a good idea because we're repeating several characters. Also, ideally, a primary key should not change. So its value should stay the same forever. So this email column is not a good candidate for a primary key because a student can change their email later on. So in situations like this, we introduce a new column, which we call an ID column, and we use that as the primary key. So double click the table. Here I'm going to add a new column, student underline ID. By default, we use the int or integer type, which allows us up to 2 billion records. And that is pretty sufficient for most scenarios. But don't take this as a hard and fast rule. Always think about the context. All right, now press tab. Let's mark this as a primary key. Now you can see that whenever we check this box, not null gets checked by default because a primary key must have a value to identify each record uniquely. Now, by convention, we should always put the primary key first. This makes it easier for us to understand our design. So here on Mac, unfortunately, we don't have drag and drop, but we can right click this and click move up. Let's do it again and again and again. All right, now we need to add a primary key to the courses table. So Once again, we cannot rely on any of these attributes or columns. So we need to add a new column called course ID. So course ID of type integer, and this is going to be a primary key. And by the way, I forgot to check this primary key as an auto increment column because we want MySQL to automatically generate values for this column. This just makes it easier for us to insert records in this table. We don't have to worry about the uniqueness of values, okay? Now, let's move this up. So back to the students table. Here's our student ID column. Let's also check this as an auto increment column. Beautiful. Now, what about the enrollments table? We're going to look at that next. Now, before we add a primary key to the enrollments table, let's talk about the relationship between the students and enrollments. Because here we have two options for adding a primary key in the enrollments table, and you will see that in a second. So here we need a one-to-many relationship between these two tables, so a student can have multiple enrollments. Here on the left side, you can see the icon for a one-to-many relationship. Now, whenever we add a relationship between two tables, one end of the relationship is called the parent or the primary key table, and the other end is called the child or the foreign key table. In this case, the students table is the parent or the primary key table because we cannot have an enrollment without having a student first. So the student is the parent, right? Now, when adding a relationship, here we need to select the foreign key table first. If you forget that, you can simply look at the status bar. The status bar says, select the table to receive the foreign key. So here I'm going to select the enrollments table first, and then I'm going to select the students table. Now, as you see, we have a one-to-many relationship between these two tables. Beautiful. Now, the moment I added this relationship, MySQL Workbench added a new column here, students, underline student, underline ID. This is basically telling us that this column is referencing the student ID column in the students table. So this is how we know who this enrollment is for. Anytime we insert a record in this table, we store the ID of that student in this column. Now, personally, I don't like this naming convention. I don't like to prefix this column with the reference table. Of course, there are situations where this clarifies the design, but in this case, I think it's unnecessary. So let's double click this table and rename this column to student ID. Now you can see that this column is marked with this red diamond because this is a foreign key in the enrollments table. So a foreign key is a column in one table that references the primary key of another table. Okay? Now let's close this window. We need to repeat this step one more time to add a relationship between these two other tables. So one more time, one-to-many. We select the foreign key table first and then the primary key table. So you can see we have another column here, courses, underline course, underline ID. Let's rename this as well. Okay, that is better. Once again, you can see in our physical model, we have more details than a logical model. At that level, we didn't have to worry about primary keys, foreign keys, because these are implementation details. Now we are ready to add a primary key in the enrollments table. And here we have two choices. One way is to use the combination of student ID and course ID to uniquely identify each enrollment. So we can use a composite primary key here. The other approach is to introduce a new column called enrollment ID, just like student ID and course ID. We can set it to auto increment. Which approach is better? It really depends. There is no hard and fast rule. The benefit of this composite primary key is that it prevents us from accidentally enrolling the same student in the same course twice, because the primary keys of a table cannot be repeated. They have to be unique. Each primary key uniquely identifies each record in a given table. So if we use a composite primary key here, we can prevent bad data from being inserted into this table. That's the benefit. What's the problem? The problem is that if we have another table in the future, and there's going to be a relationship between the enrollments and that new table, these two keys need to be repeated in that table as the foreign key, just like the student ID in this table. So when we added a relationship between the students table and enrollments table, MySQL automatically added the student ID column here as the foreign key. So if we add another table here in the future and establish a parent to child relationship between these two tables, these two keys will have to be repeated in that table. Now, depending on the context, this is not always a bad thing. Depends on the amount of data that you have and whether that table also has another child table. Now, on the other side, if we introduce a new column here like enrollment ID, we're not going to have that problem. So if you have another table here in the future and there is a parent to child relationship between enrollments and that table, we only have to repeat the enrollment ID. So we're repeating one value, one integer instead of two integers. Okay. However, currently we don't have such a table in our design. So there is no need to design for what if scenarios that may never happen in the future. So in this case, I personally prefer to use a composite primary key here because we get this immediate benefit. We can protect this table from bad data. And honestly, we don't really have that child table here, so we don't have to worry about these two keys being repeated somewhere else. If that happens in the future, we can always come back and revisit this design. We can write a change script to update the design of our tables, and that's not a big deal. So let's double click this table and move these two columns on the top. So move up. I know this is really painful. So, all right. Now we tick the primary key checkbox for each of these columns. And this gives us a composite primary key. Whenever you have a foreign key in a table, you need to set the constraints on that foreign key. And that basically protects your data from getting corrupted. So here I've got the enrollments table open. How many foreign keys do we have here? We have two foreign keys. One is the student ID that references the student ID in the students table. And the other is the course ID that references the course ID in the courses table. Now, the combination of these two columns forms the primary key in this table. Okay. Now, if you look down below, we have this tab, foreign keys. Here you can see we have two foreign keys in this table. Each foreign key has a name. By convention, we use FK, underline foreign key table, underline primary key table. So the first foreign key is for the relationship between the enrollments and the students table. So you can see this foreign key is referencing the students table. The second foreign key is enrollments to courses 1. Now, sometimes MySQL automatically adds a 1 or a 2 at the end to prevent this name from clashing with another foreign key in this database, because all foreign keys have this name and this name has to be unique in your database. Now, currently, we haven't really generated anything and we're dealing with only 3 simple tables. I know that we don't have another foreign key with this name. So I'm going to rename this and remove 1 from the end. That is better. Now look at the first foreign key. This foreign key is on the student ID column in this table. Now look at the right side. Here we have 2 drop-down lists for what should happen when the corresponding record in our parent table gets updated or deleted. For example, what should happen when the ID of a student changes from 1 to 2? Well, earlier I told you that we should not change primary keys. That's considered a bad practice. But in the unlikely event that the primary key of a table changes, we want to make sure that the foreign key table is updated. So if the ID of a student changes from 1 to 2, we want to make sure that all the enrollments for that student also get updated, so they reference student ID 2. So in this drop-down list, we select Cascade. And with this, MySQL will automatically update the records in the child table if the primary key changes. Now here we have a few other options. One is restrict, and this will reject the update from happening. The other option is to set null. So if the ID of a student changes, this will set this foreign key to null. And with this, we'll end up with the child record, in this case, the enrollment, that doesn't have a parent. We call this an orphan record. We don't want to have any orphan records in our database because orphan records are bad data. We don't know who this enrollment is for. So most of the time, you never use this option unless in very specific scenarios. And the last one is no action. And this is exactly the same as restrict. It prevents or rejects the update operation. Now, what about the delete scenario? What should happen when we delete a student? Well, we can set this to cascade, and this means the enrollments for this student will automatically get deleted by MySQL. Shall we do it? It depends. Depends on the context. In this case, we are storing financial information in the enrollments table. So we're storing the price each student paid to enroll in a course. If we delete the enrollments of our students, we're not going to be able to answer questions like how much we have sold over time or what courses were popular. So in this case, we want to prevent this delete from happening. In other words, if a student has at least one enrollment in this database and we try to delete that student, we want MySQL to prevent or reject the delete operation. So back to our foreign key constraints panel, I'm going to set the value for onDelete to restrict or no action. Both these will reject the delete operation. So whenever you have a foreign key, you need to set these two constraints and tell MySQL what should happen when the primary key gets updated or deleted. As a rule of thumb, we should always cascade on update. And for delete, it really depends. Most of the time, you want to reject the delete operation because you don't want to lose data. But in some cases, it doesn't really matter. It's okay to cascade delete. For example, let's say we have an application for people to set reminders for themselves. So they sign up, create an account, and set reminders. If someone deletes their account, we probably don't care about their reminders. You want to delete them. But don't take this as a hard and fast rule. You should always check with the business. That's why I told you it's really important to understand the business requirements. Maybe the business says, no, we don't want to delete any reminders because we want to use them to create reports on historical data. So always check with the business. Now we need to apply the constraints for the other foreign key, course ID. So I'm going to set update to cascade and delete to no action. So if a course has at least one enrollment record, we should not be able to delete that course unless we delete the enrollment first. So far, we have done a lot of work on this physical data model. But before we go ahead and generate our database tables, we need to make sure that our design is optimal and doesn't allow redundant or duplicated data, because redundancy increases the size of our database and complicates the insert, update, and delete operations. For example, if the name of someone is repeated in many different places and they decide to change their name, we'll have to update several different places. Otherwise, we'll have inconsistent data, and this is bad because it gives us invalid reports. So that's where normalization comes to the rescue. Normalization is the process of reviewing our design and ensuring that it follows a few predefined rules that prevent data duplication. There are basically 7 rules, also called 7 normal forms, and each rule assumes that you have applied the previous rules. Now, for almost 99% of the applications, you only need to apply the first 3 normal forms, and that's what you're going to learn in this section. You really don't have to worry about the other normal forms. So, over the next few lectures, I'm going to explain each normal form, and then I will give you a simple, pragmatic advice that helps you easily create normalized databases without having to remember any of these rules. So next, let's take a look at the first normal form. The first normal form says that each cell in a row should have a single value and we cannot have repeated columns. Now look at the tags column in the courses table. Here we're violating this rule because we're going to store multiple tags in this column and separate them using a comma. So we're going to have multiple values in this cell or attribute. What if we have multiple columns like tag 1, tag 2, tag 3? Well, the problem with this approach is that we don't know ahead of time how many tags each course is going to have. What if in the future we want to add the 4th tag to a course? Then we'll have to come back here and modify our design. Plus, there is no guarantee that this will not happen again. So this approach is not scalable. And this is why the first normalization form says that we cannot have repeated columns. To solve this problem, we need to take this tags column out of this table and model it as a separate table called tags. And then we'll add a many-to-many relationship between tags and courses. So let me add a new table here. Let's rename this to tags. Now we need to add a primary key to this table. We're going to call that tag ID. Now, what should be the type of this column? Well, it depends how many tags we're going to have in this database. And that's a question we need to ask the business. Are these tags going to be created by end users or the admins? If they're going to be created by end users, it's likely that they're going to grow pretty quickly. But in this case, let's assume that these tags are going to be created by our admins, and we're going to have only a maximum of 50 to 60 tags. So we can use a tiny int for this column. Now, when we try to add another column, MySQL Workbench automatically changes this back to integer. This is because I think there is a bug in MySQL Workbench. It acts a little bit flaky at times. So to fix this, you need to set the data type over here. So back to the first column, make sure to select that. Then type tiny int here and remove the parentheses. Enter. Okay, now it's updated here. Next, we need to add the name column, and we set its type to varchar of 50 to be consistent. And obviously, we need to mark this as not null. Beautiful. So here's our tags table. Now we need to add a many-to-many relationship between the courses and the tags tables. And that's a topic for the next lecture. So now we need to add a many-to-many relationship between the courses and tags tables. However, in relational databases, we don't have many-to-many relationships. We only have one-to-one and one-to-many relationships. So to implement a many-to-many relationship between these two tables, we need to introduce a new table, which we call a link table. And we're going to have two one-to-many relationships with that table, exactly like the enrollments table here. So before we introduce the enrollments table, logically we had a many-to-many relationship between the students and the courses. Then we introduced this link table. And as you can see here, we have two one-to-many relationships with this link table. We need to follow the same approach to implement a many-to-many relationship between these two tables. So I'm going to add a new table here and call it course tags. So course underline tags. This table determines the tags for each course. So in the courses table, we only have the courses. In the tags table, we only have our tags. And in this new table, we know the tags for each course. Okay, so enter. Here's our new table. Now we need to add our relationships. So I'm going to select this one-to-many relationship. First, we need to select the child or the foreign key table. And then we need to select the parent or the primary key table. There you go. Now we have a one-to-many relationship with our link table. Let me scroll to the right. That's better. Now, one more time, I'm going to add another one-to-many relationship here. First, the child table, and then the parent table. Now you can see in this link table, we have two new columns, courses underline course ID and tags underline tag ID. Let's simplify the column names. So I'm going to rename the first column to course ID and the second column to tag ID. Now in this table, once again, we're going to have a composite primary key because the combination of the course and tag ID should be unique. So I'm going to mark both of these as primary key. So link tables are very common in relational databases. Sometimes they only have these two columns, but in other cases, they have additional columns, like our enrollments table. Now let's review our design one more time. So we introduced this new table here, and now we can remove the tags column from the courses table. All right, here are the columns. Let's right-click this column and delete it. With these changes, our database is now in the first normal form. Because first of all, we don't have repeating columns like tag 1, tag 2, and tag 3. And we also don't have multiple values in a column. So all our tags are stored here in one place. If we need to rename a tag, this is the only place that we need to update. Only one record in the tags table. In contrast, in the previous design, because we repeated tags as strings in the courses table, we had several occurrences of each tag. We could have front end repeated in so many different places. Then if we wanted to rename front end to something else, like let's say we wanted to add a hyphen in the middle, we would have to update several courses records. And as you know, every time we have an update or delete operation, MySQL locks one or more rows. So with the previous design, our rows had to be locked unnecessarily. Why should we lock a course if you want to rename a tag? That doesn't make sense. If you want to rename a tag, the tag row should be the only row that should be locked. Next, we're going to look at the second normal form. All right, now let's look at the second normal form. Here is the academic definition on Wikipedia. To qualify for second normal form, a relation must be in the first normal form, and it should not have any non-prime attribute that is dependent on any proper subset of any candidate key of the relation. What is this supposed to mean? Let me make it super simple for you. The second normal form says that each table should have a single purpose. In other words, it should represent one and only one type of entity, and every column in that table should describe that entity. Here's an example. Our courses table has these columns: course ID, title, and price. So it has a single purpose. It stores course records. Every column in this table is an attribute of a course. So these columns describe a course, right? Now, what if we had a column here called enrollment date? We talked about this earlier. This is not really an attribute or a property of a course because a course can have several students and each student will probably have a different enrollment date. So this column doesn't really belong to this table. It's not an attribute of a course. It's an attribute of the enrollment. That's why earlier we introduced the enrollment entity and added the date attribute there. So the second normal form says that every column in a table should describe the entity that the table represents. If we have a column here that describes something else, we should take that column out and put it in a separate table. As simple as that. Let's look at another example. We have this orders table with these columns: order ID, date, and customer name. This table is not in the second normal form. Why? The purpose of this table is to store our orders, right? So order ID and date are attributes of the order and they belong to this table because they describe an order. But the customer name column describes a customer, not an order. With this design, if a customer places multiple orders, their name will be repeated and this will create two problems. The first problem is that we're going to waste space. The second problem is that our updates are going to be painful because if you want to update the name of a customer, we'll have to change it in several places. So this column doesn't really belong to this table. We should take it out and put it in the customers table. Now, this customer's name is stored in a single place. We have not wasted space, and if we need to change this name in the future, there is only a single record that we should update, okay? This is our second normal form. Now, sometimes this is not very obvious at first. For example, what if the column was called customer instead of customer name? You would say, well, every order has a customer, so this is an attribute of an order. So this column should belong to this table. But with this design, the name of our customers is going to get duplicated. Whenever you see that, that means your design is not normalized. So that's when you should ask yourself, where is that single place that we need to store the customer name so it's not duplicated? It's in the customers table. So we need a separate table to store all our customers. Then we reference our customers by their ID in the orders table. And that's why earlier I told you that primary keys should not be updated. So yes, we have duplicated the customer ID in this table, but that's a minimum duplication. We are duplicating integers that are 4 bytes long, not customer names that can be 50 or 100 characters long. Now take a look at the current design of our database. This design is violating the second normal form. In one of our tables, we have a column that shouldn't be there. So pause the video and think about this for a few seconds, but don't make any changes yet. When you're done, come back and let me show you how to put this database in the second normal form. All right, so our courses table is violating the second normal form because this instructor column here doesn't really belong to this table. If the same instructor teaches multiple courses, their name is going to get duplicated in this table. So we'll have to change it in multiple places. That's when we ask ourselves, where is that single place where we need to store the name of our instructors? It's the instructors table. So I'm going to add a new table here. Let's call it instructors. Here we're going to add 2 columns. The first one is instructor ID. What data type do we need here? Again, we need to ask the business. I don't think we're going to have 2 billion instructors, so the int data type is a little bit too big for this column. So I'm going to go with small int, which allows us to store up to 30,000 instructors. But again, I'm just making assumptions here. You should always ask the business. Now, let's also mark this as an auto increment column. Next, we add the name column of type varchar of 50. And this is not going to accept null values. Beautiful. So we're done with this table. Now we need to delete the instructor column in the courses table and add a one-to-many relationship between the instructors and the courses. Take a look. So in the courses table, I'm going to right-click the instructor column and delete it. Then I'm going to apply a one-to-many relationship here. So here's our one-to-many relationship. First, we select the child table or the foreign key table, and then the parent table. Now, our model is getting a little bit convoluted, so we can go to the Arrange menu on the top and select Auto Layout. That is a little bit better. So we have the instructors table over here, and here's our courses table. Now, we can see that the moment that we added this relationship, MySQL added our foreign key column. Let's rename this column to something shorter and easier to work with. So we're going to call this instructor ID. Now, because we have a new foreign key here, we need to go to the Foreign Keys tab and set the foreign key constraints. For updates, I'm going to cascade. For delete, I'm not going to take any action. So if an instructor has a course, we're not going to be able to delete that instructor. All right, now let's talk about the third normal form. Here's the classic definition on Wikipedia. So our entity or table should be in the second normal form to start with, and all the attributes in the table are determined only by the candidate keys of that relation and not by any non-prime attributes. Jesus, that's a mouthful. Let me explain it using a simple example. Look at this invoices table. Here we have 3 columns: invoice total, payment total, and balance. Do you agree that we can calculate the balance by subtracting the payment total from the invoice total? So balance can be derived from these 2 columns. We say it's dependent on these 2 columns, which means if the value of these columns changes, the balance has to be recalculated, right? Now, what if we change one of these values but forget to update the balance? Our data will not be consistent. If we look at this record, we won't know what the actual balance is. Should we rely on the value in the balance column or subtract the payment total from the invoice total? We won't know. So the third normal form says that a column in the table should not be derived from other columns. So in this example, we should drop the balance column. We don't really need it. Here's another example. Look at this table. We have first name, last name, and full name. The full name column should not be here because it's violating the third normal form. We can always calculate it by combining the first and last names. So the third normal form, just like the other normal forms, helps us reduce duplication and increase data integrity. Now here's my pragmatic advice for you. Don't worry about memorizing these normalization rules like what is the first rule or the second rule and how they're different unless you're preparing for your college exam and you have to answer stupid questions like these. These questions have no applications in the real world. When working on real projects with other people, just focus on removing redundancy, not applying normalization rules one by one to each table and each column. Nobody is going to debate with you whether a given table is in the second or the third normal form. So whenever you see duplicated values and these values are not foreign keys like 1, 2, 3, 4, that means your design is not normalized. What normalization form it violates doesn't really matter. Nobody cares about this stuff. Just think about how you can eliminate the duplication. Here's an example. We have this customers table with 3 columns: customer ID, name, and shipping address. If there is a requirement to support multiple shipping addresses, we're going to have a problem with this design. For a given customer, we have to repeat their name to add multiple shipping addresses. Now, this is a simplified table, but what if we had 2 other columns here like email and birthday? To store multiple shipping addresses for this customer, we would have to repeat all these other values as well. That's bad. How can we solve this? Well, First, we need to think about the logical entities and the relationships here. We have two entities, customer and address, and there is a one-to-many relationship between these two entities. A customer can have many shipping addresses, but a shipping address is for one and only one customer. Now we convert this logical model to a physical model. We end up with two tables, customers and addresses. The customer table has columns like customer ID, name, and email. So the shipping address column no longer exists here. Now we have a separate table for it. See what I did here? I didn't think about any normalization rules and how to apply them by moving columns around. I only thought about the logical entities and the relationship. So if you follow the same process, you really don't need to worry about normalization rules. Start with the logical or conceptual model first. Don't jump into creating tables. You will almost always end up with a bad and messy design. Also, once again, I want to emphasize the importance of the requirements. In this example, I assume that there is a requirement to support multiple shipping addresses. With this requirement, the original design violated the third normal form. But what if we didn't have this requirement? This design would be perfectly valid. So don't apply normalization rules blindly. Always take the requirements into account. And that brings me to my next point. Don't model the universe. We'll talk about that next. One of the mistakes that a lot of data modelers make is they try to generalize their model so they can support future requirements. Most of the time, these future requirements that these people think of are just in their head. They may never happen. So they end up creating a model that is overly complex and, in my opinion, useless. In one of the companies that I worked at before, we had one of these people. He tried to model the entire universe. He forgot about the scope of our project. He forgot about the context. He forgot about the requirements. So he gave us a data model that was spread over 20 pages or more. And quite honestly, nobody really understood this data model except himself. Everything was super generalized, and his argument was that this model could handle all future requirements without any changes. He also designed another database for us that took abstraction and generalization to the next level. So we had three tables called entities, attributes, and values. And again, his argument was that this model was so flexible, so general that we wouldn't need to change it in the future. Because with these three tables, we could model any concept. Because everything is an entity. So we could store it in the entities table. And everything has attributes. So we could store its attributes and values in the attributes and values tables. Now, the actual model had a few more tables like relationships, relationship types, and so on. So he essentially built a relational database on top of a relational database. This design is referred to as the sixth normal form. And while it may promise some benefits on the paper, in reality, it creates a big mess that nobody can clean up. That is the reason I told you that we had stored procedures that were 1,000 lines long. Because if I wanted to select a student record, I couldn't just write a query like this. There was no such a thing as the students table. One record in the entities table represented our students table. So I had to join this with entity instances table to get a specific student. But then I had to join that with the attributes and values tables and then do a group by. God, it was so painful. The simplest query was 10 lines long, and it was super slow. Some queries took a minute to execute, sometimes even longer. So here's what I want you to take away. Develop the best solution for today's problems, not future problems that may never happen. In the real world, people may change their legal name. Don't add a previous name column in your customers table unless it's really important to your problem domain. People move houses. Don't worry about supporting multiple addresses if all you need to know is the customer's current address. So don't build a model for the universe or the real life. Build a model for your problem domain based on the current requirements, not what happens in the real life. Don't make these kind of assumptions like, what if this happens? What if that happens? What if none of this happens? You will end up with a design that has a lot of baggage that you have to carry for a long time. And this will prevent you from going faster. It will make it harder to add new features to your applications. That's why I told you that you're going to end up in a big mess that nobody is going to be able to clean up. So as I always say, keep it simple. Simplicity is the ultimate sophistication. Don't be proud for designing a complex model. That is not something to be proud of. You can be proud only if you take a complex model and simplify it and simplify it and simplify it like no one else. And then you have a beautiful model that supports today's requirements in an optimal fashion. Your code will be beautiful, it won't be complex, your queries will execute quickly, everybody will understand your design, and you can easily extend your model to support future requirements. Don't be afraid of changes. Changes will happen whether you predict them or not. And trust me, no matter how much experience you have, you're never going to be able to predict all future requirements because they depend on the business, what the CEO thinks, not what programmers think. So once again, don't try to predict all future changes. Whenever there is a change in the future, you can always write a script to change your database model and migrate the data if necessary. And trust me, you will do that no matter what. Even if you predict all the future requirements, there is still one day that your prediction will fail. So we have created this physical model, but this is just a model. It's not a database. In this lecture, I'm going to show you how to convert this model to a real physical database. So with the physical model open, on the top, let's go to the database menu and select Forward Engineer. In this dialog box, we have to select our connection. By default, you should have the connection that you have on MySQL Workbench homepage. If not, you can select it from here. Leave all the default settings as they are. You may have to enter your password in case it's not stored here. Again, that's pretty straightforward. Now let's continue to the next step. On this page, we can set the options for the script that this wizard is going to generate. Most of the time, you want to leave these settings as they are, unless you know what you're doing. So let's go to the next step. Now here we can select the kind of objects that we want to be scripted. So far, we have only created tables in our physical model, but we can also create views, stored routines like stored procedures and functions, as well as triggers and user objects. For now, we don't have to worry about these other objects. Also, here we can select Show Filter to exclude one or more tables from being scripted. By default, all tables are selected, but we can exclude one or more of these tables by selecting them here and moving them to the list of excluded objects. I'm going to take this back to the list of objects to process. Let's continue to the next step. So this is the script that this wizard has generated for creating our database, our school database with all its tables. For example, on line 14, we have this create schema statement for creating a database called school. Below that, we have a create table statement for creating the students table. And here are all the columns in this table. For now, don't worry about the details of these statements. You're going to learn about them later in this section. Now here we also have two buttons below this script. One is save to file. So you can save this as a script file and check it into your source control repository. You can also copy it to clipboard and then go back to MySQL Workbench and paste it into a query window. In this demo, I'm going to click on the Continue button, so this wizard will generate this database for us. Continue. All right, now it's ready. So back to our local instance. Here I'm going to refresh the Navigator panel. There you go. We have the school database, and here are all the tables that we designed earlier in this section. So we have created this database. Now, what if you want to make any changes here? What if you want to add a new table or modify one of the existing ones? Well, we can always come here and open these tables in the design mode and make any necessary changes. We can add a new column or rename one of these columns or drop them. That totally works, but it only works if you are the only person using this database. In other words, you can use this approach if you're working with a database on your machine and no one else is going to use it. You're using this database for your personal reasons. But in medium to large organizations, we often have multiple servers that simulate the production environment. The production environment is where our users access our applications or databases. So in addition to the production environment, we also have staging environment, which is very close to the production environment. We also have the testing environment that is used purely for testing. And we also have the development environment. Each environment has one or more servers. So anytime we developers want to make any changes to these databases, we should be able to replicate the same changes on other databases. So all these databases that we have in various environments are consistent. How do we do that? Well, back to our model. We start here. we make our changes and then synchronize this model with the database. Let me show you. So here in the enrollments table, I'm going to add a new column. So I've selected this, and here I'm going to add a column called coupon. Let's say this is the coupon that the student is going to use at the time of the enrollment. I'm going to use a varchar of 50 for consistency and leave this column as nullable because not everybody has access to a coupon at the time of enrollment. So this is the change I've made in this model. Now we go to the database menu on the top, and instead of selecting forward engineer, we select synchronize model. We use forward engineering when we don't have a database. So we take a model and we generate a new database, okay? Now that we have a database, we want to synchronize this database with our model. So we select synchronize model. And on this page, once again, we select our connection. So here I'm connecting to a database on my local machine. If I'm a developer in an organization, I have access to the testing environment, to the staging environment, and maybe the production environment. So here, instead of selecting this local instance connection, we can select a connection to a database in the testing environment, okay? Now, let's continue to the next step. We leave all the default settings as they are. So here, MySQL Workbench detected that we are working with this database, school. All right, so we select this. In the next step, it detects the tables that need to be updated. So because I updated the enrollments table, here we have this green arrow, but because the enrollments table is associated or related to the courses table, this table might be affected as well. So as you will see in a second, MySQL Workbench has to temporarily drop the relationship between these two tables to apply the necessary changes in the enrollments table. Now we have the same story between the courses and course tags tables. So because these two tables are related, MySQL Workbench has to temporarily drop the relationship between these two and then enable it again. So let's continue to the next step. In this script, you can see a bunch of alter table drop foreign key statements. These are used for dropping the relationships between our tables. Down below, you can see we have an alter table statement. Below that, we have add column coupon of type varchar 50. So first, these relationships are disabled. Then we add a new column to the enrollments table. And finally, we enable these relationships. All right, now, once again, we can immediately execute the script to see our changes, but a better approach is to save this script in our file system and then check this into a source control repository like Git. With this, we know exactly what changes we have made to our database, and we can replicate the same change to other databases. All we have to do is to execute that script on those database servers, okay? Now, in this demo, we don't want to worry about that, so I'm going to execute the script to synchronize my database with my model. Done. Now back to our navigator panel. Let's refresh and take a look at the enrollments table. Now we have a new column called coupon. What if we want to change a database that doesn't have a model, like our SQL Store database? This database doesn't have a model like our school database. How can we change this database? That's really easy. The first time we need to do this, we need to reverse engineer this database to create a model. We'll use that model for any future changes. So first, I'm going to close this model that we created earlier in this section. This is really important because when we reverse engineer this database, if a model is already open here, MySQL Workbench will add this database to that model. Now, this is not a big deal, but it's better to have a separate model for each database. You can include multiple databases in one model, but that's something you want to do if these databases are highly related and you want to work with them in the same model. So our model is closed. Now on the top, we go to the database menu and select Reverse Engineer. So you can see MySQL Workbench automatically created a new model. In this model, we don't have any diagrams. So here on this window, we're going to select our connection. And then we select the database that we want to reverse engineer. So I'm going to select the SQL Store database. As you can see, we can select multiple databases. But once again, do that if these databases are highly related and you want to work with them in the same model. Now let's continue to the next step. All right, so here it's asking us if we want to import all the 7 tables in this database. Just like before, we can select Show Filter to exclude one or more tables. We don't want to do that because we want to add all our tables to our model. So let's execute this. All right, now here we have a new diagram that is added to our new model. It's right here, okay? Now back to the diagram, you can see all our tables and their relationships. This is really helpful in understanding our database design. For example, here we have a one-to-many relationship between the products and order items. We can also use these diagrams to identify the problems in our design. For example, somewhere over here we have this table, order item notes. As you can see, this table is not related to any other tables. What is the problem here? The problem is that we can insert any values in the order ID column, and MySQL Workbench will not validate that. So we want to have data integrity. When we add a relationship between our tables, MySQL Workbench will enforce the integrity of our data. So in our child tables, we can only add values that correspond with the values in our parent tables. So currently we don't have any relationships here, and that means we can insert invalid values in the order ID and product ID columns. So these diagrams are really helpful. They help us better understand the design. They help us identify the problems, and they allow us to make any changes to this design and then script those changes to execute on other MySQL databases. All right, here's a project for you. I want you to design a database for a flight booking system. Download the PDF I've attached to this lecture. In this PDF, you can see an example of a ticket that this system should generate. Based on the information you see here, design a database for this system. You will see my solution next. All right, this lecture is going to be very informal. I haven't done any prep work because I just want to walk you through my thought process and show you how I approach a data modeling problem. So here on Draw.io, I'm going to create a conceptual model using entity relationship diagrams. So what entities or concepts do we have in this domain? We have the concept of flight, passenger or traveler, aircraft, airline, airport, and so on. These are the concepts that I immediately see in this domain. So let's add an entity for each. Here's the first one. I'm going to call this passenger. You could also call it traveler. It doesn't really matter. Here's another entity. We're going to call this flight. So a passenger books a flight. Now let's add a relationship between these two entities. Here we have a bunch of relationship options like one-to-many, one-to-one. At this point, we don't really care about the type of these relationships. We just want to add a relationship between our entities. We'll clarify each relationship when we build our logical model. So for simplicity, I'm going to use a many-to-many relationship for all relationships in this demo. Here's one. I'm going to add this between passenger and flight. And then I'm going to add a label to this relationship, books. So passenger books flights. Now let's add a few attributes to these entities. What do we need to know about each passenger? Well, based on the requirements, we need to know their name. That's the only thing we need to know about each passenger. Now in the real world, we also need to know their email, their address, their date of birth, and maybe other attributes. But none of those attributes exist in the requirements I have given you. So we want to stick to the requirements. We don't want to model the universe or the real world. We want to do enough modeling to solve a business problem. So name is sufficient for now. What do we need to know about our flights? Each flight has a number, so let's add that here. We need to know when a flight is going to happen. So here we need a date time attribute. Well, more accurately, we need to have two date times. One is the departure date time, the other is the arrival date time. So let's rename this to departure date time and arrival date time. Also, let me zoom in a little bit more. Okay, that is better. All right, what else do we need to know about a flight? We need to know its duration. So let's add that here. We also need to know the distance. So in the example I've given you, the flight between Los Angeles and San Francisco is just over 200 miles. That is the distance. We also need to know the airline that operates a flight. Now we can add the airline as an attribute here, or we can model airline as a separate entity and then add a relationship between flight and airline. That is more of a normalization thing because we don't want to repeat the airline's name in the flight. But at this level, we're still doing our conceptual modeling, so we don't have to worry about normalization. We can always come back to it later. So let's get the basics right. What else do we need to know about each flight? We need to know the departing and arriving airports. Now, each airport has a bunch of attributes. One of them is IATA code, and that is the 3-letter code that you see in this example. For example, LAX is short for Los Angeles International Airport. So airport is really a separate entity because it has its own attributes. So I'm going to add another entity here. Let's call that airport. Now, this airport has a IATA code. It also has a descriptive name like Los Angeles International Airport. It's located in a city and state and country. Now, technically, we don't have country in our example, so this is actually out of scope. We only want to focus on city and state. If you want to support international flights, we can always come back and modify this model. So this is the airport. Now we need to add a relationship between flight and airport as well. Once again, I'm going to add a many-to-many relationship. This is purely for simplicity. We'll refine the type of these relationships later when we build a logical model. So let's add this here and attach it to the flight as well. All right. Now let's give this relationship a label. Departs/arrives at. Now here on page 1, we see the ticket number for each passenger. Where should we put that attribute? It doesn't belong to a passenger, neither does it belong to the flight. It's actually an attribute of the relationship between these two entities. So it's part of the booking. So I'm going to add a new entity here. Let me move this around and put it on the top. That is a little bit better. Unfortunately, we have a limitation of space here. Please bear with me. So I'm going to call this booking. This booking is going to have a ticket number. It also has a price that you can see on page 3. That is the amount each passenger pays for a given flight. Now, in the real world, we also need to keep track of when this person made this booking. So the booking entity should also have a datetime attribute. But again, we don't see it in the requirements at this point. So I don't want to complicate this model by adding things that we don't need yet. So here's the price attribute. Now on page 2, you can see that both these tickets are in economy class. So that is another attribute of this booking. Let's call that flight class. Now we could also call this booking ticket. So we could say a passenger purchases or books a ticket for the flight. That is more of a naming issue. Conceptually, we have an entity like ticket or booking that has these attributes: ticket number, the price the passenger paid, and the flight class, which can be economy, premium economy, first class, and so on. So now let's delete this relationship and recreate it through the ticket entity. So once again, I'm going to add a many-to-many relationship. This looks a little bit funky. Sorry about that. All right, here's our relationship. Let's attach one end to the ticket, the other end to the passenger. That looks good. So we can add a label here like purchases or books. In my opinion, they both work, but sometimes these words have different meanings in the heads of domain experts. So you should always check with them. The whole point of this conceptual model is to make sure that we developers or data modelers and domain experts are on the same page. We use the same language, the same words. So for now, I'm just going to call this purchases. Now, let me refine this relationship. It doesn't look properly attached here. Okay, that's better. So here's our ticket entity. Now let's add another relationship from ticket to the flight. So one more time. All right, so here's the relationship between the ticket and the flight. Let's give it a label. So a ticket is issued for a given flight. Now there's one more attribute that we need to add to the ticket, and that is the confirmation number. So let's add that here as well, confirmation number. All right, so here's our conceptual model with these 4 entities based on what we know about this problem right now. Next, we're going to build a logical model based on this conceptual model. All right, now we want to refine a few things to build a logical model. The first one is the relationships between these entities. So let's talk about the relationship between passengers and tickets. A passenger can buy many tickets, but each ticket is issued for only a single passenger. So here we have a one-to-many relationship between the passenger and the ticket. So I'm going to open up the right panel, select this relationship, and change one end from many to one. There you go. So we have one to many. Now, what about ticket and flight? Again, here we have a one-to-many relationship because each ticket is issued for a particular flight, but a flight can have many different tickets. So I'm going to select this relationship and change this second end to 1. So we have a one-to-many relationship between flight and ticket. Next one. What about the flight and airport? Well, each airport can host many different flights, but each flight works with 2 and only 2 airports. Now, in entity relationship diagrams, we don't have 2, we only have 1 and many. So we can still treat this relationship as a many-to-many relationship because a flight deals with multiple airports and an airport hosts multiple flights. Now let's set the type for each attribute. So IATA code is going to be a string. Let's type that here. Name is also going to be a string. Also city and state. What about flight number? Well, in this example, we're dealing with a 4-digit number. But sometimes airlines use a combination of letters and numbers, so number is technically a string. Departure date time is going to be a date time. We need both the date and the time. Same is true for arrival. What about duration? Well, we can measure duration in seconds, minutes, hours, or even days. In the case of flight, it's better to measure the duration in minutes because we might have a flight that is, let's say, 35 minutes long. We don't care about the seconds, we only care about the minutes. So I would prefer to rename this attribute to duration in minutes. This is more descriptive. Nobody is going to guess what this number represents. Is it the seconds? Is it the hours? Is it the days? It's very clear. So duration in minutes, and this is going to be an integer. What about the distance? This is also going to be an integer. But here I want to rename this attribute to distance in miles. So again, there is no guesswork. And we can also convert this number and display the distance in kilometers if we want to. Next, we have airline. We can set the type of this attribute to a string. But with this structure, we're going to end up duplicating the name of the airline. So it's better to represent airline as a separate entity that has a code or a number as well as a name. So let me bring back our design panel and add a new entity here. We're going to call this airline. Airline. All we need to know about each airline right now is their name. This is going to be a string. Now we should add a relationship between the flight and the airline. Each airline has many flights, but each flight is operated by a single airline. So we have a one-to-many relationship. Where is that here? It's over here. All right. Now let me move this around. So we have a one-to-many relationship between the airline and the flight. And with this, we can remove the airline attribute from here. That is better. All right. The name of each passenger is also a string, but here we want to split this into the first name and the last name. So first name is going to be a string. Last name is going to be a string as well. What else do we have here? Finally, the ticket. So the ticket number right now is a 10-digit number. We're not going to perform any calculations on this number. This is just a label. So I'm going to use a string for this. Price is going to be float because we have a decimal point. Flight class, again, here we can use a string, but we'll end up duplicating the flight class. So it's better to model this as a separate entity. So I'm going to add a new entity here. Move it on the top. Let's call this flight class. Now, I'm not entirely sure if this is called flight class in this domain. This is one of those cases that you need to talk to the domain experts to see what they call it. So for now, let's just add the name attribute here. And then we need to add a relationship between these two entities. Now, a ticket is issued for a particular flight class, but a flight class can have several tickets. So here we have a one-to-many relationship. So here's the one-to-many relationship between the flight class and ticket. Finally, we need to set the type for confirmation number. Again, this is going to be a string. Now, back to our airport entity. With this design, we'll end up duplicating the city and state and potentially the country. So shouldn't we take out these attributes and model them as separate entities like countries, states, and cities? So a country can have multiple states and a state can have multiple cities. That is the proper normalized form. So in theory, yes, this is better. We reduce data duplication. But the problem with this is that our data will end up being so fragmented. Quite often, if not always, we need to join these 3 or 4 tables together to look up airports in a given city. These joins can hurt the performance of our applications. So in situations where we want to improve the performance, we should denormalize our tables. So tables that are frequently joined together, we combine them into a single table. This is one of those examples. With this design, we don't have to constantly join these tables together. And take into account that we're not going to have a million airports in the world. We have a limited number of airports. Not every city has an airport. So the duplication we're dealing with here is not a big deal. So in this particular case, I prefer to denormalize our design and add the city and state attributes here. And one last thing before I finish this lecture. Here we have a many-to-many relationship between the airport and the flight entities. But as I told you before, in relational databases, we don't have many-to-many relationships. We only have one-to-one and one-to-many. Whenever you have a many-to-many relationship, you need to break it down into 2 one-to-many relationships. And we do that through a link table, a table that represents the relationship between 2 entities or 2 tables. Now here we can add a link table, but the problem with that link table is that it allows a flight to have an association with more than 2 airports. Because with a link table, we can have a many-to-many relationship. But as I told you before, each flight only deals with exactly 2 airports. So in this particular case, I prefer not to use a link table. And instead, I prefer to add 2 attributes here: departure airport, arrival airport, just like departure date time and arrival date time. So let's add those here as well. Departure airport, let's say ID. This is going to be the ID of the departure airport. So an integer. And also arrival airport ID, also an integer. So when we build a physical model based on this logical model, we'll need to add foreign keys on these 2 columns. So here's our final model. You can download this as a PDF right below this video. This is just based on what we know about this problem right now. So don't take this as the best or as the only solution for this kind of problem. There is no such a thing. Every solution has pros and cons. This is what I have come up with during this modeling session. Tomorrow, if I look at the same problem, I will come up with a different solution. The chances are my solutions are going to be very similar or even identical. But the point here is that as we learn more about the problem, about the business domain, our model changes. Just one last thing. I noticed that here in the ticket entity, I forgot to remove the flight class attribute after I added the flight class entity. So let's delete this from here. Okay. We're done with this model. I hope you learned a lot. I leave it up to you to build a physical model for this because that's very repetitive and I already showed you the steps earlier in this section. All right, now let's work on a second project. Download the PDF I've attached below this video. In this PDF, you can see the requirements for an application called Vidly. This application is going to be used at a video rental store. If you have seen any of my other courses like my React course or Node or ASP.NET MVC, you're definitely familiar with Vidly. In all these courses, we focused on building the actual application, including the front end and the back end. But in none of these courses, we spent time designing the database. So I thought to bring Vidly in this course because it's a fantastic exercise for you. And quite honestly, this was a suggestion by one of my good students, Muhammad. He's very dedicated and has taken several of my courses. And I believe with such dedication, he's got a lot of success ahead of him. So Muhammad, if you're watching this, thank you for making this suggestion and I send you my best wishes. So download the PDF below this video, read the requirements, and design a data model for this application. You will see my solution next. All right, once again, I'm going to take a very informal approach and take you through my thought process. So let's look at the requirements document and figure out the entities we have in this domain to build our conceptual model. So we need different levels of permissions for different users. So that tells us we probably have two entities here, permission and user. So let's go back to draw.io and add a couple of entities here. User and permission. So user can have multiple permissions. Let's add a relationship between the two. Once again, for simplicity, I'm going to go with a many-to-many relationship. We don't care about the type of the relationship at this stage. We'll refine this when we get to our logical model. So a user has permissions. Now back to the document. So the store manager should be able to add, update, and delete the list of movies. So these are our permissions. They'll be in charge of setting the stock for each movie as well as the daily rental rate. So this will happen at the time of adding or updating a movie. Cashiers should have a read-only view of the list of movies. They should be able to manage the list of customers and the movies they rent. All right, let's move on. Now at checkout, a customer brings one or more movies. So here I see two entities, customer and movie. These are the entities that we need to know about in this domain. So let's add them to our diagram as well. Customer and movie. So what is the relationship between these two entities? A customer rents one or more movies, right? So let me add this here. So customer rents movies. Now, back to the document. The cashier should look up a customer by their phone number. So phone number is one of the attributes of a customer. If the customer is a first-time customer, the cashier asks their full name, email, and phone number. So these are the attributes of each customer that we need to know. Let's add them over here. So name, email, and phone. Now here we can use Pascal convention by capitalizing the first letter of every word, or we can use camel notation. Earlier I used camel, then I changed it to Pascal. It doesn't really matter. This is just for brainstorming. This is for communication. All right, back to the document. The cashier then scans the movies the customer has brought to checkout and records them in the system. Each movie has a 10-digit barcode printed on the cover. So barcode is an attribute of the movie. Let's add that here. Barcode. Now back to the requirements. When the customer returns to the store, they will bring the movies they rented. If a movie is lost, the customer should be charged 5 times the daily rental rate of the movie. So for each movie, we need to know the daily rental rate. Let's add that to our movie entity, daily rental rate. Now, the cashier should mark the movie as lost, and this will reduce the stock. So stock is another attribute of the movie. For each movie, we need to know how many of them we have in the store. Let's add that to our model. We can call it stock or number in stock. Now, back here, there is no need to keep track of lost movies. All we need to know is the number of movies in stock and how much the customer was charged. For other movies, the customer should be charged based on the number of days and the daily rental rate. So for each movie that a customer rents, we need to know how many days the customer has rented this movie and then multiply it by the daily rental rate. Now, this number of days, what entity this attribute belongs to? Back to our model, we can put that on the customer because a customer might rent several different movies. By the same token, we can add it here because each customer might rent a movie for a different period. So that attribute is an attribute of the relationship between these two entities. So now we need to introduce a new entity and call it rental. This represents the relationship between these two entities. And that means we need to delete this relationship and recreate it through this new entity. So let me add a couple more relationships here. All right, so we've got the rental entity here. For this, we need to know the number of days. Now to calculate the rental fee, we get this number and multiply it by daily rental rate. If a movie is lost, we assume 5 as the number of days and multiply it by the daily rental rate. Okay, back to the requirements. We issue discount coupons from time to time. The customer can bring a coupon when returning the movies. So coupon is another entity. Perhaps each coupon has a code like ABCD and a discount value. So somewhere in our system, we need to register the coupons that we have created. Perhaps the store manager or the cashier can do that. Unfortunately, here, the requirement doesn't tell us who's going to do that. So for now, let's not worry about that. But what matters is that we're going to introduce a new entity here. Let's call it coupon. This coupon is going to have perhaps a code, maybe some description, and a discount. And this coupon can be applied to a rental. So there's a relationship between the coupon and the rental. There you go, like this. So let's rename this relationship to applied to. All right, now back to the requirements. It is possible that the customer returns the movies they have rented in multiple visits. That basically means I might rent 5 movies. Tomorrow I will return 2 of them. The day after I will return the other 3. And finally, we need to be able to track the top movies, top customers, and revenue per day, month, and year. So this is just a rough conceptual model that helps us understand the problem. Now, one thing that we didn't add here, and it was not reflected in the requirements, was the attributes of the user. What do we need to know about each user? Well, at a minimum, we need to know their username and password so they can log in into the system. What about permission? Each permission should have a description, like add movie, update movie, and so on. So we've got these 2 entities on the top. And below this, we've got these 4 entities: customer, movie, rental, and coupon. Next, we're going to refine this model and build our logical model. All right, now we need to think about storage. Is this model a good model for storing the data in this application? Let's find out. So let's talk about the users and permissions. First, we're going to specify the type of the relationship between these 2 entities. Here we have a many-to-many relationship because a user can have multiple permissions, and the same permission can be applied to different users, many-to-many. But there is a problem in this model. The problem is that every time we register a user, we have to explicitly assign those permissions to that user. For example, today we have one cashier. Let's call it cashier number 1. We need to give this cashier 10 permissions. Tomorrow we hire a new cashier. We have to come back and give this new cashier these exact 10 permissions. The problem here is that we may give one cashier an extra permission, or we may forget to give them one permission that they really need. So the issue is that our cashiers or store managers are not going to have a consistent set of permissions. Each user has different set of permissions. So we have to make sure that our users have consistent permissions. Now back to our requirements document. Nowhere in this document we were asked for the flexibility to assign specific permissions to each user. So this model is too fine-grained for this application. It's suitable for an application where we want to have full control over the permissions of each user. So we need to change this model and introduce a new entity called role. We want to put our users in roles or groups like store manager or cashier, and then assign permissions to those groups. Next time we register a new user, we simply add that user to a specific group or role, and that user will automatically inherit all the permissions in that role. With this change, our users will have a consistent set of permissions. So let's add a new entity here. All right, so here's our new entity, role. Each role should have a name. Now we need to assign a user to a role. So let me move this relationship to here. A user belongs to one role. We don't want to add users in multiple roles because nowhere in the requirements we were asked to do so. So let's change this end of the relationship to 1. That is probably the drop-down list on the right side. Let's take a look. That was right. So a role can have multiple users, but a user belongs to one and only one role. Beautiful. Now, we need to add a many-to-many relationship between roles and permissions. A role can have multiple permissions, and a permission can belong to multiple roles. But before we do this, let's go back to the requirements document and have a closer look at the kind of permissions we need here. Basically, we have the store manager that can do everything, and we have cashier that can do everything except managing the list of movies. So the cashier can only view the list of movies. They cannot add, update, or delete a movie. That is the only difference. So in my opinion, this model is a little bit too fine-grained and too specific for this kind of requirement. We don't really need a table like permissions with records like add movie, update movie, delete movie, add customer, update customer, delete customer. This is very fine-grained. We don't want that level of control. For example, we don't want to have a role where a user can add a movie but not update a movie. See where I'm going with this? We don't need that level of control here. So in my opinion, we really don't need this entity. All we need to know is the role of the user. And in our application, we can write a simple if statement. If the user is a store manager, we will enable all features. Otherwise, if they are a cashier, perhaps we're going to hide certain features or disable them, like adding a movie, updating a movie, and deleting a movie. That's all we need, nothing more. So let me give you a metaphor. Imagine you're traveling and you need one room to stay for one night, and your budget is $100. Let's say you're a single person. All you need is a simple room with a single bed. Now you come to me and I say, hey, I have a room. It's actually a suite. It's huge. It has a king size bed. It has the view of the ocean. It has a balcony. It has jacuzzi. It has Wi-Fi and video games, but it costs you $500 a night. Would you pay for that room? You probably wouldn't. All you need is a simple room to stay for one night and your budget is $100. You're not going to spend extra $400 for the features you don't need. Building software is the same. All these additional features that you predict that may happen in the future, somebody is going to pay for it. That is the company. So don't over-engineer. Don't ruin people's money because of the features that you think are necessary. Now, this is not all about money. It's about managing complexity. In this design, I don't want to bring extra complexity because this complexity is going to stay there for the lifetime of this application. Every time we need to fix a bug or introduce a new feature, we'll have to deal with unnecessary complexity that inexperienced people have brought into the design of this application. So let's delete the permission entity here. We don't really need it. All we need is a simple role table. Now let's set the data types. Both the username and password are going to be a string. The name of the role should also be a string. Beautiful. Now for the customer, these are all strings, so I'm not going to waste your time typing them. Barcode is going to be a string because we're dealing with a 10-digit number. Daily rental rate is going to be a float because you might have a number after decimal point. So let's set that here. Number in stock is going to be an integer. Now when it comes to building a physical model, we're not going to use the integer data type in MySQL because that would allow us to store up to 2 billion. We're not going to have 2 billion copies of a movie in a store. So the maximum number we need here is probably 50 or 100. We can use a tiny int for that. Now let's look at the rental. We need to know the number of days. Here I'm going to remove this attribute and replace it with two date time attributes. The date somebody rented a movie and the date they returned it. With this, we can calculate the revenue per month, per day, and per year. That was one of our requirements. With this design, we cannot calculate the rent for a given time period. So let's break this into two attributes. Let's say rent date and return date. Both are either date time or date. I don't think in this domain we care about the time. Perhaps the date is sufficient. Now we can subtract these two values and calculate the number of days. Now, each rental can have a maximum of 1 coupon. So this end of the relationship should be 0 or 1. So I'm going to select this relationship and then change the right end to 0 to 1. So here's the icon. That is 0 to 1. Now in physical terms, in a physical model, that means we're going to have a table called rentals. In that table, we're going to have a column called coupon, and this column is going to be nullable. Okay? So a rental can have a maximum of 1 coupon, but a coupon can be applied to many different rentals. Beautiful. Now, what about the relationship between the rental and the movie? Each rental is for one and only one movie, but the movie can be part of many different rentals. So this end of the relationship should be 1. Let's set that here. I'm not entirely sure if it's the left one or the right one. It depends on how I inserted the relationship. All right, that worked. So we have a one-to-many relationship between the movie and the rental. By the same token, a rental is for a specific customer, but a customer can have multiple rentals. So this end of the relationship should be 1. Let's set that here as well. There you go. So one-to-many. Also, here in the customer entity, I'm going to break the name attribute to first and last names. That is better. So we're done with our logical model. Now I leave it up to you to build a physical model for this in MySQL. So you have learned how to use the wizards in MySQL Workbench to create and modify databases. These tools are really helpful and they increase our productivity. But if you want to become a database administrator, you need to understand the script that these tools generate. So every time they generate a script for you, you need to review it and make sure it doesn't have any bad impacts on your database. So over the next few lectures, we're going to look at a few more SQL statements like create database, create table, and so on. Once you learn this, you'll be able to create databases or modify them by hand without relying on these visual tools. So in this lecture, we're going to look at 2 statements. One is create database for creating a new database, and this will be an empty database without any tables. Now let's give this database a name like SQL_store2. Let's execute this. Now, here we have this new database. If we execute this statement one more time, we're going to get an error. So a better approach is to include if not exists keywords here. So create database if not exists. And now we can execute this multiple times without getting an error. We also have drop database for deleting a database. But here we remove the not keyword. So drop database if it exists. And now our database is gone. I'm going to recreate it one more time because we're going to use it over the next few lectures. So create database if not exists. Next, we're going to look at the create table statement. In this lecture, you're going to learn how to create a table. For this demo, we're going to recreate this customers table that we have in our SQL Store database. We're going to recreate it in our SQL Store 2 database. So the first step is to use this new database, SQL Store 2. Then we type create table. We give our table a name, customers, and then we add parentheses. And inside this parentheses, we list all the columns. So what columns do we have here? We have customer ID. Let's type that here. Next, we add the data type for each column. This one is going to be an integer. We want to make this a primary key. So we type that here as well. And also, we want to apply the auto increment attribute. So MySQL automatically generates a new value every time we insert a new record here. So we add the column name followed by its data type and any attributes that apply here. Let's add another column, first name. This one is going to be a varchar of 50. And here we want to apply the not null attribute. So every customer will have a first name. Now, I'm not going to add all these columns here because that would be a waste of time. So let me add the key ones that help you understand how this statement works. I'm going to add another column. Let's say points. This one is going to be, what is the data type for this? We can select that here. And right below the schemas panel, we have this object info panel. Unfortunately, it's not visible here. But in this panel, we can see the data type for this column. That is an integer. So let me add that here. Now, I want to apply the not null attribute here as well, but I also want to give it a default value of 0. So we type default 0. Now let's add one more column here, email. This one is going to be varchar of 255. It's not going to be nullable, and we want to make sure that every customer has a unique email. So here we can apply the unique attribute. So here are the attributes that we can apply to each column. Primary key, auto increment, not null, default, and unique. Now let's terminate this with a semicolon. Now let's execute the script. Beautiful. So if we refresh the navigator panel, we should see this new table. So SQL Store 2, we have our customers table. However, we're not able to re-execute this script Because we already have this customers table in our database, and when we try to recreate it, MySQL will yell at us. So just before this, we can write drop table if exists, customers, and then we can create this table. There is also another approach. So instead of dropping the table, we can say create table if not exists, customers. Now let's execute the script one more time. We can execute it as many times as we want without getting an error. Beautiful. Next, I'm going to show you how to modify a table. In this lecture, you're going to learn how to modify an existing table. So let's say we created this customers table, but we realized that we forgot to add the last name column here. Or maybe we chose the wrong data type for a given column. This is where we use the alter table statement. So I'm going to open up a new query window here. And in this window, we're going to alter the customers table. So we type alter table customers. Now here we can add a new column. So we type add, give our column a name, last name. Data type, just like before, varchar of 50. Here we can apply any attributes like not null, unique, default, and so on. Now, if we execute this, MySQL will add this column at the end of this list of columns. But that's not what we want. We want to add this after the first name. So here we type after first name. Like this. Now, if you have a space in your column name, which you shouldn't have to start with, you need to wrap your column name with backtick, like this. So if you have a space here, we'll have to use backticks to indicate the column name. But once again, you really shouldn't have a space in your column names. That's just an ugly naming convention. All right, so I'm going to revert this back to what we had. Now let's execute this statement. Back to the navigator panel, refresh. So here's our new last name column. Beautiful. Now, when writing an alter table statement, we can make multiple changes in one go. For example, we can add a new column, remove an existing one, and also change the data type or the attributes of one or more columns. So before terminating this statement, we can add a comma and add another clause, like add, let's say, city of type varchar of 50, and this is not going to be nullable. Now we can modify an existing column, for example, modify column. Now this column keyword here is optional. You don't have to type it, but some people prefer to be more explicit. So they type add column, modify column, and drop column. But again, it's optional. So modify column, first name. We can change its data type to varchar of 55. We can also give it a default value of an empty string. And finally, we can drop an existing column. So drop, let's say, points. So this is how we can alter or modify a table. But remember, do not ever alter a table in a production environment because that can have really bad consequences. Always try your changes on a test database, make sure they work, make sure they don't have any bad impacts, and then execute them on a production database. Next, I'm going to show you how to create relationships. Now let's create the orders table and add a relationship between the customers and orders. So I'm going to collapse the customers table so we have more space here. First, we're going to drop the orders table if it exists. So drop table if exists orders. And then we create the orders table with these columns. First, we need the order ID. This is going to be an integer and it's going to be the primary key for this table. Next, we have the customer ID. This is also going to be an integer and it's not going to be nullable. So here I apply the not null attribute. Now let's clean up this code by aligning these attributes. That's better. Now note that here I did not apply the not null attribute on the order ID column because when we apply the primary key attribute on a column, MySQL will assume that that column does not accept null values because it doesn't make sense to have null in a primary key column. Now, to define a relationship between these two tables, after we list all our columns, we type foreign key. So we want to apply a foreign key constraint on the customer ID column. First, we need to give our foreign key a name. Here's a convention that a lot of people use. FK, underline. Here we add the name of our child or foreign key table, that is orders, and then we add the name of the parent or primary key column, customers. Next, in parentheses, we list the columns that we want to add this foreign key on. In this case, the customer ID column. Now here we need to tell MySQL that this column references the customer ID column in the customers table. So we type references, customers table, and in parentheses, we type customer ID. So that's the customer ID column in the customers table. Next, we need to specify the update and delete behavior. Should we cascade them or reject them? What should we do? So we type on update. Here we can type cascade or set null or no action. These are the options that you saw earlier in the foreign key panel. Let me show you. So here in our SQL Store database, let's take a look at the orders table. And by the way, I'm looking at the original SQL Store database. So I open this table. Down the bottom, we have a bunch of tabs. Open the foreign keys tab. And here you can see all the foreign keys, the columns they're applied on, and the update and delete behavior. So back to our query window. If the ID of a customer changes, I want to cascade the update so the corresponding customer records in the orders table get updated automatically. So here we type cascade. What about deletion? On delete. I don't want to cascade the deletes because I don't want to accidentally lose our orders. So here I'm going to use no action, and this will prevent or reject the deletion. If you try to delete a customer and that customer has an order, MySQL will say, hey, you cannot delete this because there is an order for this customer. Now, some people argue that we should not cascade updates because the primary key should not change. While I agree with that in theory, in practice, things are different. We don't live in a perfect world. Sometimes the primary key can change. This can be someone's accident. It can be a bug in our application. It can happen for a number of reasons. So I personally prefer to cascade my updates. But if you disagree with this, that's totally fine. Now, let's terminate this statement with a semicolon and execute our script. All right, beautiful. Let's refresh the Navigator panel and look at our SQL Store 2 database. Here's the orders table that we created. Beautiful. Now, if you re-execute this script, we're going to get an error on line 3. MySQL will not be able to drop the customers table because now it's part of a relationship. So to delete the customers table, first we need to delete the orders table because this table depends on the customers table. If we delete the orders table, customers table will not be part of a relationship and we can easily delete it. So I'm going to move this drop table statement before dropping the customers table. We can separate these statements by a line break. That's better. Now let's execute the script one more time. Beautiful. Our database is regenerated from scratch. In this lecture, you're going to learn how to drop or create relationships between tables that already exist. For example, let's say in our current script, we forgot to add the foreign key constraint to the orders table. So we forgot to create the relationship. Now I'm going to show you how to add this relationship after creating the table. So back to our other query window. Earlier, you learned about the alter table statement. You learned how to add, modify, or drop columns after creating a table. We can use the same statement to add or drop the foreign keys in a given table. So alter table orders. Here we can drop the existing foreign key. So drop foreign key. What is it called? FK, underline, orders, underline, customers. Now, at the same time, we can drop or add another foreign key. So let's add a foreign key called FK, underline, orders, underline, customers. We're going to add this on the customer ID column. So here we're following the exact same syntax that you saw in the last lecture. So we type foreign key, we give it a name, we specify the column and all the other attributes. So we say this foreign key references the customers table. And here we need to add the primary key in that table. And finally, we specify the update and delete behavior. So on update, cascade, and on delete, no action. Now here we have a red underline because I forgot to add a comma here. Now here we can also add or drop primary keys. Let me show you. So we type add primary key. In parentheses, we type the name of the columns that are part of this primary key. In this case, order ID. Now if you have multiple columns, we can separate them using a comma. And finally, we can drop a primary key like this. So when dropping the primary key, we don't specify the name of the columns.